My name is Professor Volk, and today we're talking about some foundational statistical concepts. We're going to talk about different types of vocabulary and answer some other questions involving bias and sampling methods. Just to give you an introduction, this aims to provide a comprehensive overview of the essential statistical concepts, but only to get you started. We're going to talk about things like the dual meaning of the term statistics, as well as the importance of representative samples. Each section, we're going to have a little bit of a quiz, a concept check, and then we're going to follow up with some interactive case studies at the end. So let's get started with some statistical terminology. A population in statistics is the entire group you wish to study. However, one example of that would be all registered voters in a country, which sounds familiar because when we say population, a lot of times we're talking about people in a country or people in a particular area. However, population in statistics just means the big group. So we could be talking about all NFL games. All NFL games that have ever been played in the NFL. That is a big group, and we might be looking at the games that took place just this year, for example, as a smaller group of a bigger set. So a population in statistics isn't always people, a lot of times it is, but it is the big group, the entire group you wish to study, even if you're not looking at everything in that group. A sample is the subset of the population you have chosen to represent it. The subset of the population that you are actually going to be studying and analyzing when you're doing your statistics. For example, rather than ask every voter in the country what they think, you actually might just survey 1,000 voters as a representation of all the voters, because asking everybody would take a little bit too long. Then we have something called a population parameter. That's a numerical value like mean or standard deviation that summarizes the entire population. For example, the average height of everyone in the United States might be a population parameter. However, that doesn't necessarily mean something that we can actually know the answer to. We know that it exists. There is an average height of the American citizen. However, how we would calculate that seems a bit more complicated. And that's why we use statistics to represent population parameters, these unknown true numerical values that are just difficult to know the actual answer. Which is why we use sample statistics, numerical values, and that summarize the sample as a representation that serve as an estimate for population parameters. Now, population parameters is a numerical quantity that represents the true value for the entire population. And since that's often hard to calculate or get our hands on, we might use a sample statistic as just an estimate. Quick concept check. What is a population in statistical terms? A group of people living in a specific area. B, the entire group that you wish to study. C, a sample subset. Or D, the researchers conducting the study. The answer here, population, is the entire group that you wish to study. We need to mention that statistics, even when we're talking about statistics, actually has two meanings. The first meaning is statistics as a discipline, which is the science of data collection, analysis, interpretation. In other words, I study statistics, or I took a course in statistics. Statistics is a method for doing science, specifically one that looks at data and how you analyze and interpret that data. However, a lot of times people use statistics to actually mean something more specific. Statistics also is used to represent numerical facts. So when we say the statistics say, what we're saying is these are the facts. This is the statistics. These are the specific numbers derived from the data, such as a city's median income or the average age of a freshman student at a certain university. Those are just numerical facts that we could actually calculate and find the answer to. Quick concept check. How is statistics defined as a discipline? A, numerical facts only. B, the science of organizing parties. C, the science of collecting, analyzing, and interpreting data. Or D, the art of making graphs? The correct answer here is the science of collecting and analyzing and interpreting data. When we're calculating statistics and we're doing our analysis, we want to use a representative sample. It's very often difficult to get every single person in the country or in a population for us to get the data. So we might want to use a smaller subset, a smaller sample. However, it is important that we use a representative sample, a sample that represents the overall population. By using a representative sample, it increases the validity of our statistical conclusions. It ensures that the conclusions are accurate and that they represent the population that we're talking about. One example of a valid measure would be using a random sample for political polling. We're going to talk more about how we get those representative samples. But for now, what we need to recognize is that it is important to understand whether the group that they used as a sample actually represents the larger group. If the sample is representative of the whole population, we're allowed to say that it is generalizable in many cases. If a sample, for example, we wanted to ask ourselves about all the voters in a particular country, but our sample, we only surveyed women over the age of 65. And then we say, well, based on our survey, based on our sample, we can make a conclusion about how voters are going to vote in the election. The truth is that isn't generalizable because we've only surveyed a subset of the population. We haven't surveyed a group that represents the overall population. We want to make sure we have some young people, we have some middle-aged people, we have some old males, females. We want to make sure we mix up our diversity in a way that represents the population. Otherwise, drawing conclusions based on a sample that doesn't represent our population will lead us to making invalid conclusions. Some common sampling methods, in other words, how do we pick the groups and how do we decide who's going to be included in our small subset? Some common sampling methods include simple random sampling, stratified sampling, cluster sampling, convenient sampling, and systematic sampling. Each of these have their pros and cons. However, I am going to tell you that the best case scenario is simple random sampling. When you have a study that is using simple random sampling, it is more generalizable and more representative of the population. Simple random sampling, by definition, is a method in which every individual in the population has an equal chance of being included in the sample. For example, if you have a list of 1,000 employees in your company, you could randomly pick, using a random number generator, 100 employees for a job satisfaction survey. Let's say you didn't want to send it to all 1,000 employees, so you wanted to pick 100 employees. You shouldn't just pick the 100 employees that earn the most or the 100 employees that are the easiest to get a hold of. It would make sense, if you're not going to survey everybody, to make sure you have a nice random sample. And you want to do that in a way that's simply random. In other words, you don't say it's random because I picked every other person that walked in the door. We say it's random because we use random numbers to pick our sample. Stratified sampling tries to get a sample that goes across the entire population, but it doesn't necessarily pick them randomly. For example, let's say you wanted to make sure you were getting voters on a political poll that would represent voters across the country. Then you might choose a stratified sampling method where you make sure you randomly select voters within each state. So you make sure you have voters from each state to represent in the survey. Now, that is not the same as simple random sampling, because if you did simple random sampling, you wouldn't necessarily randomly pick 100 people in every state. And you could argue that picking 100 people in every state would give you data that would not necessarily result in strong conclusions if you were assuming you wanted the general voting consensus. For example, 100 people out of the population of Wyoming is a big difference as opposed to 100 people out of the population of Florida or Texas or California. Cluster sampling is a way that you might divide a geographical area or a bunch of groups into clusters and then randomly pick a group or one cluster to include in your sample or survey. An example might be if you wanted to survey teachers about mental health resources, you could send out a survey to every teacher in the country. However, you could instead pick randomly 10 schools in a district or in a state or in a region, and based on those 10 schools, survey every teacher in that school. Now, this isn't the same as simple random, right? Because depending on which 10 schools you pick, you might have radically different answers. But the benefit of doing cluster sampling is that you're able to follow up and make sure you get 100% participation or as close to it within each cluster. However, the negative is that which cluster you end up picking could greatly affect your outcomes. Convenient sampling is convenient. That's its key feature. It's convenient for who? It's convenient for the researcher. It asks, how am I going to get the number of people in my survey or in my study? Where am I going to get the people? And instead of rather than trying to make it a random sample or making sure you're covering everybody, you go, I need 100 people to fill out my survey. I'm just going to go to downtown and walk the streets and just get the first 100 people I can get to fill out my survey. Now, that might be the quickest way to do it. Although, who's to say that surveying those the first 100 people you see, or the first 100 people that are willing to fill out your survey when you approach them on that street, is going to represent the population as a whole? It probably won't. So you got to be careful when using convenient sampling, and it is one of the biggest red flags I see at beginner survey design and beginner research studies is people don't pay close enough attention to how they get the people for their sample, and the default is usually to go with the most convenient option for the researcher. That means that their conclusions are not going to be very solid, and they probably aren't going to be generalizable at all. Systematic sampling is the last sampling method we're going to mention today. Systematic sampling involves selecting individuals at regular intervals from a sorted list of the population, and also having a starting point that's generally random. So, for example, rather than survey the first 100 people that walk into the supermarket when you're trying to get a sense of the average shopper, if you were to survey the first 100 people that walk through the door, then you're getting a bunch of early bird people that shop early in the morning. What you might want to do is spread that out a little bit by instead researching and asking every 10th shopper. Now, what this does is it provides a little bit of randomization into it because it spreads out the people that you're getting a sample from. So this is more positive than straight up convenient sampling and just saying we're going to take whatever we can get and whatever we can get as easy as we can get it. This takes a better approach. You see this a lot of times in quality control. If you were to take a sample of a product coming off of an assembly line and you wanted to do a quality check, a lot of times you'll use a systematic sample. In fact, you'll say, well, we're going to check every 100th car that comes off the product line, and we're going to do a deep inspection to see if there's any mistakes. We're going to check every 100th car. And if every 100th car is good, then we're going to say there's no errors, this is working great. Although, note that means there's 99 cars in between that we didn't check. So it doesn't mean it's going to check everybody, and it also assumes that we're going to catch the patterns by getting every 100th. It's not quite random. So we could have had something that broke down for 50 cars in a row on the assembly line, and then somebody fixed it, and we don't ever catch it because we were checking every 100th car. And so just recognize that systematic sampling is a step up from convenient sampling, but in a way, it's just another way you can do something that's pretty convenient for the researcher without necessarily providing the appropriate level of rigor to draw generalizable conclusions. Quick concept check. Why is a representative sample important? A, it's easier to manage. B, it ensures the validity and generalizability of conclusions. C, it supports the researcher's bias. Or D, it makes the study look more impressive. Well, the answer here is that it ensures the validity and generalizability of conclusions. It hopefully isn't too difficult to manage, but if we go with the easiest to manage, then we're not going to pick the best possible statistical outcome for our sample. Let's talk about understanding bias and the impact that bias can have on our surveys and our research studies. And when we're picking samples, we need to understand how our bias might be affecting research. So bias is a systematic error that affects the study validity. And its impact is that it undermines the credibility and affects decision making. And if you have a bias that you're not controlling for in research, because we all have biases, if you're not controlling for your biases and you're not aware of what they might be, then you're going to be allowing them to infect your data. Let's look at 4 types of bias. There's a lot more we could talk about, but these are 4 big ones. The first up is selection bias. And this bias occurs when the sample chosen for a study isn't representative of the entire population. This can lead to inaccurate or skewed conclusions. Let's look at 3 examples. First, in political polling, you want to make sure you survey everybody or a representation of everybody instead of just serving, for example, people who live in the suburbs, who might be ignorant of the perspectives of rural voters in the country or urban voters in the cities. In medical trials, for example, if you only pick young and healthy volunteers, then it won't necessarily generalize to older and sick populations who might need the medication or might need the intervention that you've been studying. The next up is response bias. Here, participants are the ones that are providing inaccurate and untruthful answers, which affects the study's validity. However, there are a few things we can do as researchers to limit this response bias. Some examples of response bias include when people exaggerate their charitable donations to appear altruistic. You might be leading them in the right direction, but they might be naturally tending to give the wrong answer, an untruthful answer. Another one might be if you lead them in the wrong direction. For example, if you leading question, don't you think our service is great? Can you influence respondents to agree with that? Yeah, if you promote it, like, don't you think, or do you agree? And they are more likely to agree instead of asking them a neutral question. The other might be people that just agree with all survey statements, regardless of their actual views. They might just say, agree, 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 and that's not really giving you an honest perspective. Another type of bias, the third one we're going to talk about, is observer bias. This happens when a researcher's beliefs or expectations can influence their data collection or their interpretation. Some examples are when you don't use double-blind trials. Now, double-blind trials is a procedure that leads to favorable outcomes for a treatment that researchers believe in when they don't take into account that they might be leading the patients into the right outcome. And so we want to make sure we use double-blind trials when possible. A teacher's expectations might have an effect on the outcome of their students. For example, a teacher who believes certain students are gifted actually results in those students maybe overperforming, or maybe they overlook the positive traits in other students. The other thing would be confirmation bias. Researchers who are so focused on their own hypothesis, and proving what they believe is true, that they focus on only the details that lead to that conclusion. The fourth that we're going to talk about is confounding bias. Now, this bias occurs when an external factor affects both the dependent and independent variables, clouding the relationship. This isn't necessarily that the researcher has done anything wrong. It's just that they failed to consider that there might be another thing in play. For example, a study might found that smoking and lung cancer are related at a certain rate, and they might see some relationships, but if they don't take into account the age of participants, they might go, oh, all these participants are smoking and they don't have lung cancer, so smoking doesn't cause lung cancer. But if they're only surveying 18-year-olds who have not been smoking for very long, then they might have just not shown or developed lung cancer at that point. So being aware of those other factors that might be involved. For example, dietary habits might affect or confound a study that links exercise and weight loss. You might say those who exercise lose weight, but it is worth noticing that although that might be true, the dietary habits are also in play. A quick concept quiz for you. What is observer bias? Is it A, a bias against watching TV? B, when researchers unconsciously influence the study? C, when respondents lie in their answers? D, when only certain groups are sampled? The answer here is B, when researchers unconsciously influence their study. Let's try 6 problems, practice problems, identifying our sampling method, our sample, and our population. Now, we've talked about each of these terms, so we're going to look through 6 cases, and I want you to try to answer each of them. And you can pause if you need to, and then we're going to go through the answers of all 6 questions. So here we go. Case study 1. Researchers survey every 10th shopper entering a supermarket on a given Saturday. What is the sampling method, the sample, and the population? Case 2. A political pollster surveys 500 registered voters in each state. Case 3. A researcher surveys people closest to her at a bus stop regarding what they think about public transport usage. Case 4. Students are divided into 4 groups based on their majors, and 50 students from each major group are surveyed about their study habits. Case 5. A health organization randomly selects 100 schools in a country and surveys all the teachers in those schools about mental health resources. Case 6. A study involves picking the names out of a hat from an entire list of employees at a large corporation to answer an engagement survey. Are you ready? Hopefully we've been able to look at sampling methods. You've been able to identify what is the sample we are picking, and then what is the population for each sample. The answers to those case studies are here. We've got systematic sampling, stratified sampling, convenient sampling, cluster sampling, and simple random all represented. Just notice that the samples are the smaller groups, but they're hoping to draw conclusions about the overall population. When we ask every 10th shopper on that Saturday what they think, it's not because we want to know what every 10th shopper believes. We ask that because we want to know what all shoppers at that supermarket on that Saturday want. When we ask about 500 voters from each state, it's not because we want the information about those 500 voters, it's because we want to generalize and draw conclusions about all registered voters in each state. In conclusion, we've looked now at a comprehensive overview of foundational statistical concepts, including immediate feedback through some interactive case studies. This knowledge hopefully will serve you as you go in and you take a look at more statistical research and you get started analyzing and creating your own statistical analysis.